morning, sir.
Morning, ma'am.
Sir, can we start by 10, sir?
Sure.
Okay, sir. Thank you, sir.
Thank you.
Sir,
Ma'am?
sir, can you start, sir?
Yeah, please, ma'am. I will stop.
Thank you, sir.
Ma'am, is my screen is visible, ma'am?
Yes, sir. Sir, we will
Thank you.
introduce yourself, sir.
Yeah, please, ma'am. Sure, ma'am.
On, sir.
As we embark on this faculty development journey, let's heed the words of John C. Maxwell. A leader is one who shows the way and shows the way. Let this program be a guide to our collective growth. It's a brand new day of endless possibilities. Welcome to one and all gathered here for the 5-day FDP on Empowering Educators, AI in Robotics and Automation for Innovative in Digital Era, organized by Department of Mechatronics Engineering by Sri Krishna College of Technology. I'm pleased to invite Dr. T. Mohan Raj as the esteemed chief guest, bringing the expertise, inspiration to elevate our event today. Dr. T. Mohan Raj is currently working as an assistant professor in the Department of Mechanical Engineering, Amrita School of Engineering, Coimbatore campus, Amrita Vishwa Vidyapeetham University. He completed his bachelor's, BE, and master's program in mechatronics engineering at Kungu Engineering College, Erode. He completed his PhD in mechatronics engineering field at Anna University, Chennai in 2018. He has more than 10 years of academic experience and he is currently working in AI and ML condition monitoring, device development for physical assistance, and design of dynamometers and autonomous vehicles. He also executed the funded project from the University Grants Commission, New Delhi, Chennai, and Sony, Japan. He is working on a research project from Sony Sensing Solution University program, and he has also received many publication awards from Amrita University for his publication in high IF and high quality journals. Welcome, sir, and we are very delighted to invite you on this FTP.
Thank you very much, ma'am. Dignitaries and all the participants for this FTP. Very good morning to one and all. So today we are going to discuss a topic on digital twins for industrial automation. So before we are moving to digital twin or any kind of industrial automations, we would like to review the progress of industrial revolutions from industry 1.0 to industry 5.0. So starting from industry 1.0 that has been initiated during the year 1800, preferably our beginning of 18th century. So there the advantage of water and steam power, we are introducing some simple mechanization with the aid of wheels and gears. We have introduced a small mechanization process. Then later we move on to the industry 2.0, a second revolution of industry during 1900 with the aid of electricity, and we have introduced the assembly line which leads for mass production. So wherever the similar kind of activities has been enhanced for n number of times, we can go with this kind of mass production. Later, during 2000, we have moved on to the industry 3.0 with aid of our PLCs, computers, robots, programmable logic controllers or our programmable automation controller. We have enhanced our systems. Here we have enhanced machine to machine connectivity, man to machine communication, and man to machine connectivity connected end to end. So that leads to industry 4.0. So before we are fully deploy or 100% implementation of industry 4.0, currently we are having industry 5.0 introduced from German. So Industry 5.0 is none other than combination of our cyber physical system along with robots. Our human involvement is also actively involved, where we are having robot collaboration, our cobots, cognitive systems, and many kind of customization. So compared to Industry 4.0 and Industry 5.0, in this Industry 5.0, we have had some sustainability in terms of no hazardous or no dangerous that has to be happen to environment or any kind of operating persons or any living things. So that will be the main emphasis for Industry 5.0 compared to Industry 4.0. So similar to Industry 4.0, all kind of technologies will support for Industry 5.0 also. So still we are in the middle stage of Industry 4.0. Other countries will move towards Industry 5.0 also. So Industry 5.0 promotes balance, diversity, and empowerment, which will be deals with human centric. So any human can work with any kind of machineries. So if you consider for human robot collaboration, if any two robots working together, in between that human can involve and participate in any kind of process, maybe in terms of assembly or machining or material handling or quality checking, whatever it may be the case, the robots will accommodate human as a part of worker without making any harmful effects or any hitting to the operator. And also it promotes for sustainability, which leads to action on sustainability and respects the planetary boundaries, which won't make any harmful effects or which won't give any dangerous or hazardous to any kind of things, especially the living things. And resilient, it is also agile and resilient with flexible and adaptable technologies. So whenever we move on to any kind of AI-based algorithms or enhancements in any techniques, that Industry 5.0 has a resilient to support all the technology changes. It is also ready to adopt any kind of changes in this era. So Internet of Things, that will be a part of our Industry 4.0 as well as 5.0. So here we have to establish a connectivity or communication between machines and tools through wireless technology. So wired communications also can be used. So if you are going to do everything through our cloud or IoT based device, wireless communication is mandatory. So currently over 50 billion things that has been connected to internet. So the term things refers to we can connect anything. A machine can be connected to cloud, a human man can be connected to cloud, any kind of our device, our laptops, mobile, wrist watches, or any kind of wearable devices, anything that can be connected to internet. So hence we call it as Internet of Things. Interconnection of all the things that will be considered as Internet of Things. So things connected to the internet are expected to cross 100 billion in near future. So as of now, we are around 100 billion devices that has been connected to internet. So it has to be increased beyond that level also in forthcoming years. So unification technologies such as low power embedded systems with our Raspberry Pi or Jetson Nano or Intel Upsquare boards or any kind of computing devices along with cloud computing, big data analytics, machine learning and networking. So networking that gives the sufficient capability for connectivity and communication between one device to another device. So with aid of all those things, we can apply Industry 4.0 as well as Industry 5.0 for any kind of applications. So this figure depicts the connected devices projection from year 2003 to 2020 obtained from Cisco. So during 2003, we have a world population will be around 6.3 billions. So in that time, we are having the connected devices as 500 million. So average connected devices per person will be 0.08. So less than 0.1. So preferably around only 8% of devices that has been connected to internet. So during year 2010, population has been increases to 6.8 billion. Connected devices change from 500 million to 12.5 billion. So we have around 1.84 connected devices per person. So almost everyone having minimal of one connected devices, that may be our mobiles or laptop or whatever it may be. So during 2015, it has been drastically increases from 1.84 to 3.47. 2020, that will be around 6.58. So per average of each person, they may have around 6 connected devices that has been connected with any kind of cloud or internet. So this will be the power or progress of connected devices. During forthcoming years, this 50 billion can be increases to 100 billions. So IoT, that's another than interconnection of physical things or any kind of operating things. Network of physical objects that contain embedded technology to communicate and sense or interact with their internal states or external environment. So IoT is none other than, simply we can say, any data we are going to push to cloud is IoT. It's not entirely IoT thing. So the system has to be communicate and sense and interact with the internal and external environment. So based on the environmental changes or any parameter that changes in the industry, according to that, it has to make a decision, or else it has to support for decision making. Only that will be considered as fully IoT based device. So simply pushing a data to cloud itself, not an IoT device. So that will be one kind of monitoring only. The system itself can perform edge computing or cloud computing, as well as based on the sensory inputs from the plant, preferably in any kind of automation industries. It has to make a decisions and deploy those decisions on the physical plant. So that will be fully automated or IoT based devices. So evaluation of connected devices starts with from our ATMs, web, smart meters, digital locks, healthcare, vehicles, smart city, and smart desk. So everywhere that has been connected. So there will be a simple example for evaluation of connected devices. IoT market share for manufacturing sector, we are having around 40%. For healthcare, we are having around 30%. Retail business like our e-shopping or any kind of online shopping mall, we have around 8.3%. For security, we are having 7.7%. So modern day-to-day IoT applications, we are having trillions of sensor supports for IoT connectivity and communications. From the trillions of sensor, we can able to develop billions of smart systems. For those billions of smart systems can be applied for million applications. So a few examples are smart parking, structural health monitoring, noise urban map, smartphone detection, traffic congestion, smart lighting, waste management or wastewater management, smart road, and so on. So I would, in order to deploy IoT, we need some few technologies. So preferably we are looking for data science or data analytics in terms of big data analytics. Then we have to make a decision making algorithm through AI or ML or any kind of deep learning algorithms. So then we have to make a connectivity between our physical devices with our cloud. So that can be enabled through Zigbee, RFID, Bluetooth, Wi-Fi, LoRa, or 6LoWPAN. So these are all the essential connectivities that are required to make a communication or connectivity between the physical world and cloud. After that, that can be deployed for several industries, preferably with a banking system or security, any kind of retail investments, manufacturing, automotive sectors, home automation, building automations, healthcare applications. So these are all the typical applications where we can apply this IoT. So common communication protocols that supports for Internet of Things or Industrial Internet of Things, 8EEE 802.15.4, 8EEE standards, Zigbee, 6LoWPAN, IP protocol version 4/6, low power wireless personal area network, wireless HART, Z-Wave, ISA 100, International Society for Automation 100 standard, Bluetooth, RFID, and LoRa. So LoRa is none other than long range, which can cover up to 6 meters from a central hub, 6 kilometers from central hub. So next we move on to digital twin. So digital twin is defined as an up-to-date representation of a physical asset while it is in operation. So that's none other than while our physical model or our physical device that has to perform any task or that is in ideal conditions, your digital twin model is also perform the same. So that's none other than up-to-date representation of a physical asset. So that asset may be a small element, small component, or a system, or our entire plant. So that's none other than our digital twin. So the digital twin can be created with many ways. So we have basic two principles. So digital twin is a virtual representation of an object or system that spans its life cycle, is updated from real-time data, and uses simulation, machine learning, and reasoning to help decision making. So the digital twin can be classified into three types: product-based digital twin, production-based digital twin, and performance-based digital twin. So the product-based digital twins can be used for creating new product designs in an efficient and effective manner. Production-based digital twins is useful in manufacturing and production planning. That can be useful to enrich or enhance the manufacturing process and production planning and layout. Performant digital twins, so that will make it as an integration between the virtual digital twin model and the physical plant to capture all the real world data from the physical plant and act it accordingly. So wherever any changes or corrections that has to be deployed on the physical asset, just we can deploy those corrections on our developed digital twin model. The same has been updated in the physical model also. Meanwhile, any changes that we made on the physical plant, the same will be tuned and updated on our developed virtual model also. So that's another than our performance digital twin. So based on this performance digital twin, one can able to monitor the plant production or overall equipment efficiency or its entire production level from anywhere. So wherever he want to change any parameters in the machine, he can simply change this in his digital twin model. The same can be applied with the physical asset also. So digital twin that may be considered for a single component, preferably a hydraulic pump in a hydraulic unit, or with the entire systems where we are having a number of hydraulic components, hydraulic pumps, motors, valves, and system of systems where we are having n number of such a hydraulic systems. So wherever we can apply it for in the component level as well as system level as well as system of systems. In any kind of applications, we can easily build a digital twin model. So the digital twin model, this case we are going to consider is, we are going to consider for hydraulic system, preferably a hydraulic pump, which is called specific type of gear pump. So from the gear pump, we are going to make some measurements using the sensors with the different operating conditions. So that may be our faulty conditions or maybe a blockage or some loose contact or some leakage, problem with the motor or problem with the pump or bearing defects. For all the simulated fault conditions, we are going to make measurements. So based on those measurements and the data, we are going to make a digital twin model. So that will be the one kind of making digital twin. So this model is considered as data-driven approach. So from that model, we can able to identify the state of the pump, whether it is in working conditions or yet to be failure, or what about its remaining useful life, what about its overall performance, everything we can predict or estimate using this digital twin. So the 5 dimensions of digital twin is, we are having a physical entity, virtual entity, digital twin data, different services, preferably our cloud services or cloud communications, and connections. So this example, we can consider any kind of physical entity, maybe a cycle or your gear pump. So you have to analyze the physical data. So what will be its actual speed? For example, if you are considering a gear pump, what about its overall efficiency, volumetric efficiency, what will be the maximum speed, what will be the fluid flow rate and pressure? We can measure through our physical entity. If it have any tendency to come across any kind of defects, with the defect also we can able to make a measurements. Then for the same data, what sort of physical device we have to make it as a virtual one. To make this as a virtual entity, we can use any kind of 3D modeling or finite element packages or MATLAB, any software which is convenient to us, we can make a virtual entity. So the virtual entity that has to perform 100% as like our physical entity. If our virtual model is not exactly fit for our physical model, then we have some residuals. So then after that, we are calculating the data from our physical entity as well as virtual entity. We have to make it as a digital twin data. So once our digital twin data has been ready, we can push to cloud in terms of our DeepSpeak or Fruit or AWS. There we can upload it and we can make a model. Then we have to establish a communication or connection between all the elements. Physical entity to virtual entity, considered as CN, physical entity and virtual entity. Virtual entity to digital twin data, CNVD. Physical entity to digital twin data, CNPD. Physical entity to service, CNPS. Digital data to service, CNSD. Virtual entity to service, CNVS. So after this will be considered as a 5 dimensions of digital twin. So here our physical plant, virtual plant, digital twin model with the cloud, and everything has been connected together. So these are all the 5 dimensions of digital twin. So this will be applicable for any kind of part, component or system or systems of system. So to create a digital twin model, we may go with 2 kind of approach. What we explained earlier, that will become under the category of data driven modeling. Another one is first principles based modeling. So this will be a physics based approach. So this will be data driven approach. In the physics based approach, you have to create a typical physical entity using your Skcet MATLAB for your electrical drive lines or multimodal dynamics or fluids. Similarly, we can use your any kind of 3D modeling packages, SolidWorks or Fusion 360 or ANSYS along with our finite element method or finite element analysis. So from that we can extract the mechanical data in terms of deformations or stress or strain. Another simplest way is if our model is smaller in size and able to make it as an exact physical model, we can go with this first principle. Otherwise, if our model is really a complicated one, where we are having a number of subsystems, we can't able to make all the subsystems together with 100% accuracy. We may go with data-driven approach. So in the data-driven approach, we are installing some sensors in the physical model or our physical entity. So example, in our gear pump, we are going to measure the speed, flow rate, pressure, and vibrations or any other parameters. What are all the things that require to estimate the model or predict our required outcomes in terms of remaining useful life or its defects or time when it needs maintenance or when it's yet to go for failure, those kind of things. What are the parameters we would like to consider? We can measure those things. So from those different parameters with the different faulty conditions, we can make a model. So this model will act as a digital twin. So the different steps involved in digital twin model with application is, first one is we have to monitor our physical plant. So from that physical plant, we have to measure the data and analyze the data with respect to which different quality conditions, what about our output in terms of performance, either the reduction in the flow rate or reduction in the pressure. Then we have to make these two things. We are going to make a data-driven model. The data can be obtained from the sensors or can be directly simulated from our first principles of the physics-based first principles. So from that, we are going to make a predictive model. So once our model has been able to predict any changes that occurs in the developed digital twin model, preferably a virtual digital twin model, then we have to make a communication between the developed digital twin model. So that's another than virtual model has to be connected and communicated with our physical model. So based on that, both will having the effective communication. So what are all the changes that happens on our physical plan that will be replicated on our digital twin model? Then we can make any kind of control actions in terms of increasing the speed or decreasing the speed, increasing or decreasing of the valve opening. So if any defects, if you are found during running conditions in the physical plant or our digital twin model, we can make appropriate optimization in terms of servicing or maintenance or replacing a particular component. Everything can be carried out. So first two parts will be considered for creating a digital twin model. These three parts will be the application of digital twin model when it can comes into real world applications. So here we are going to consider about a simple hydraulic system. So here we are having a reservoir. Along with reservoir, we are having three valves and one gear pump and one motor. So same can be created using a MATLAB Skcet model. So here we are having our motor, gear pumps with a different pressure sensor to measure the pressure value, blockage valve and leakage valve. Again, all those lines will be again connected to our reservoir as like our typical hardware. So here we are going to measure the performance in terms of pump outlet pressure as well as fluid flow. So here this will be our developed model. So this model has to be developed with respect to what are the dimensions and the maximum range we have it in our physical model. For example, the reservoir having the storage capacity of 100 liters, here also you have to make the same. If our motor will have the operating range of 1500 RPM speed, here also you have to set the similar speed accordingly for the pumps and remaining valves also. So whenever you have to going for digital twin, so that model has to be 100% digital representation of our physical model. So then only we can make exact predictions and decisions. So this is about our creation of digital model using Skcet or sim mechanics. So then we are going to make a performance with our real-time system. Similarly, we are going to check the performance of our digital twin by varying the flow rate, changing the operating speed of the motor, how the pressure and flow varies. We are getting a digital twin model. So once we check with our actual data and our digital twin data, we have to make a communication between our physical plant and our digital twin plant. So based on the communication protocol which supports either TCP, IP or Modbus, whichever is convenient, we can make a communication between this physical model and our digital twin model. So once this model has been established, now we can make a control and prediction over the hardware through our digital twins. So this output with respect to speed for pressure in valve with the different valve opening conditions through the blockage valve as well as the leakage valve. So whenever the speed increases, the pressure has to be decreased. So next part is we are going to control and predict the status. So to predict different fault based on the previous conditions, we have to label the data with the different faulty conditions. So here we are having different fault like leakage fault, blocking fault, and bearing fault. Here we are going to mention all those things. So with respect to different time frame, what we obtain the data from our physical plant as well as from our digital twin model. Since few cases we are going to simulate the fault, so we know the labels. So once we label the different faulty conditions, we can make it as a visualization using different plots. Then we can make any kind of ML or deep learning based model. Here we can use supervised learning algorithm. So once training, you can validate your model with your different performance matrices. Then your model has been ready for real-time validation. So here, if you are having around 95% plus classification accuracy, then we can easily get minimum of above 90% of classification accuracy with different fault conditions that can be occurred with our physical plant. So here we are having around 4 fault. So all the faults has been labeled. So here we are creating an AI supervised learning algorithm based model. So that has been deployed with our digital twin model. So whenever these two has been integrated, if any fault occurs, that has been easily identified with our digital twin model and that has been reported to the operator or maintenance person to make a remedial action. So once we create a digital twin model, in order to identify the remaining useful life, we are in need of calculating the RUL estimator model. So the intended use of digital twin is optimize the maintenance schedule by estimating the remaining useful life. How longer it can be useful without any damage or any maintenance, or whenever it requires any maintenance activity or any replacement. So for the purpose, we have to identify the RUL estimator. So here we are having 3 different models: similarity model, survival model, and degradation model. So similarity model is none other than when our system, say example, our gear pump will moving from healthy state to failure state. So you have to predict that well in advance before reaching the failure state. You have to give the intimation to the maintenance person and make some maintenance or remedial action to enhance the lifespan or lifetime of the gear pump. Survival model is when it's going to be failed. So if you are identifying that if the particular pump is going to be failed within 5 days or 10 days, so prior to that, we can order for any other new pump to avoid any delay in the transportation as well as any delay in the maintenance routine. So once the time has been over, we can immediately replace the pump and make it ready for further usage. So degradation model is moving from healthy state to failure state. So before it reaching the failure state, we are fixing some safest threshold value. So whenever it reaching that particular threshold limit, we can make or initiate some maintenance action to enhance its further lifespan. So these are all the 3 different RUL estimator model. So these models can be developed with our system identification toolbox or our from the physical model. So this from the physical model, we are creating a virtual model. We are going to calculate the inlet and outlet flow. So this is our typical representation of digital twin model with our physical and DT. So here we are having different faulty conditions: no fault, blocked inlet, seal leakage, or wound bearing. So if our physical plant has come across any kind of these 4 defects that has been intimated there. So based on that, we can immediately make remedial actions to avoid further delay as well as further damage for our physical plant. So that remaining useful life estimation can be performed with our physical model based on our data or using our system identification toolbox from MATLAB or any kind of data-driven approach using your Kalman filter. We can make a model. Similarly, we can make a degradation model with our preventive maintenance toolbox, so which gives the remaining useful life from the current date. So here, for example, estimated remaining useful life will be around 21 hours. So within the 21 hours, we have to replace that hydraulic pump. So based on these 3 model, we can able to identify its remaining useful life or when it requires for maintenance or when it has to be failed. So while identifying all those things, we can easily make some alternate arrangements in terms of maintenance, or we can make additional component for replacement. So those ordering can be easily carried out without making any delay. So for example, here our model will move to suboptimal state. So before it's going to reach the end of life or expected failure, we can initiate some maintenance activity. In some cases, if you are going to it should be nearer to the end of its total lifetime. We are going to replace it. We can procure the model, we can procure the required hardware or COM. We can replace it on time to avoid further delay. So if required for our systems will be complex enough, you can create hundreds of different faults. You can simulate it, predict the model with your different failures, and we can inform our maintenance stock. So after 48 hours, this kind of failures may be come for particular machines. So you can make some advanced predictive plan to attend the maintenance as well as to avoid the failures. So those kind of inputs that can be easily given to the maintenance person or our maintenance department to avoid breakdown or long time for maintenance. So now we are going to discuss about simple application of digital twin to monitor the tool conditions. So here we are going to consider the machining process, preferably end milling. So in the end milling, as like we are going to create a digital twin model based on the second approach, which is known as data-driven approach, rather than first principles of physics. So here we are going to consider the milling machine. So we can't simply make the milling machine model with any kind of softwares, maybe our FEA or 3D modeling or SimScan. So instead of that, we are going to develop a model using the sensory data that can be obtained during machining. So here we are having two sensors, vibration sensor as well as microphone, to measure the spindle vibration as well as machining sound. So based on these two things, we are going to identify the quality conditions of the tool. So we are going to consider the speed as 1800 rpm, depth of cut as 0.15 mm, and feed as 250 mm per minute. So to obtain the signal for different tool conditions, we have initiated 5 simulated tools with a different breakage. So first one will be a thrust tool, as it's new one. The second one tip has been broken, 2 tip, 3 tip, and all the 4 tips have been broken. So at the time of machining, with respect to this kind of milling cutters, we may have a possibility for failure of 1 tip, 2 tip, or 3 tip, or 4 tip, that may be considered as a catastrophic failure. So if you are going to consider for insert type cutting tools, there may be a wear. We have to consider the wear with different wear values, either in terms of 0.1 mm, 0.15, 0.2, 0.25, 0.3. So beyond 0.3, that can be useful for roughing operations or for finishing. So we may set a threshold of 0.3 mm wear for flung. Similarly, we can consider for crater wear or nose wear. So these are all the 5 faulty conditions we have simulated. So we are going to run the machine with these different 5 tools. Then we are going to make the measurements of vibration as well as sound signals. So here we are a digital twin model using different machine learning algorithm. So this work, we are going to consider the algorithms in terms of PNN, support vector machine SVM, KNN, K nearest neighbors, navy base, and random forest or random forestry. So this random forest will be a part of ensembler learner. So once with respect to our acquired data, we are going to extract the features. So once our features has been extracted, that has been given as an input to our different machine learning classifiers. So which algorithm gives the highest accuracy that can be used for our digital twin model. So these are the results of probabilistic neural network model. So here we are having the accuracy of 91.3%. So totally we are having 5 fault conditions. So first tool, 1 tip broken, and this will be 2 tip broken, 3 tip, all the 4 tips are catastrophic failure. So here we are having around 3 samples which has been misclassified as 1 tip broken, 22 samples has been misclassified as 2 tip broken, and 52 samples has been misclassified as 4 tip broken. So here we are having the true positive rate of 79.4%. Similarly for tip 1, tip 2, tip 3, and tip 4, we are having the accuracy of 99, 92.4, and 100% accuracy 86.5. So by checking these all the 5 classes, we are having the overall accuracy of 91.3%. So similarly for KNN, we are having 75% accuracy for 1 tip broken, 84% accuracy for first 2, 89% accuracy for 1 tip broken, and 100% accuracy for 3 tip, 76.5 for 2 tip. Overall accuracy will be around 76.5%. Random forest is having the accuracy of 88%. SVM having the accuracy of 82. NB we are having the accuracy of 74%. So PNN 91.3, KNN 85, SVM 82, Navy base 74, random forest 88. So this is a simple video recording how to create a digital twin model. So we develop a digital twin model. So you can select any kind of algorithm. So this will be the confused matrix for PNN. Similarly for SVM. Random forest. If you are going to visualize the data, you can load the vibration data as well as microphone data for sound signals. So here we are loading the 40 broken or catastrophic failure state. So this will be the frequency and power spectrum, amplitude with respect to number of samples. So here we are having different parameters. Here we have considered all the statistical features: mean, median, kurtosis, average, minimum, maximum, and summation. So here we have not involved any kind of feature selection process. So for testing, to validate that whether our model has predicted well, so we are considering any one kind of fault. So in this case, we are loading for fresh tool data, input data for all the 10 features we have given, and once click on that predict tool failure, we are getting the result as what kind of data we have. So this data we loaded for fresh tool, so we are getting the similar result as fresh tool. So this shows that our model will be better, which having good classification accuracy. So now we are going to enter the data. So we are going to consider for first tool. We can take any one sample and have to enter all the 10 features corresponding to a particular row. So these are all other than statistical features of the vibration signal. The tool class will be new tool. We will enter all the values, predict tool nature. We are getting the result as fresh tool. Similarly, you can check it for sound signals. Again, we are getting the similar result as first tool. So this will be the typical illustration of creating a digital twin model for condition monitoring. So similarly, we can develop any kind of model for any applications. The process may be simple machining or entire industry. A smart factory, they can deploy DCB. So here we are getting the result as first tool. So with the aid of our Simulink MATLAB, we can create a digital twin model. So inside the digital twin model, we are having our selected algorithm. We are going to feed the selected features. Here we have considered all the 10 statistical features. Everything has been fed. So our model will give the result as a classifier. 1 stands for plus 2, 2 for 1T broken. If the output is 3, that indicates for 2T broken. 4 indicates 3T broken. 5 indicates all 4T broken. So there are 5 total classes.
Anita
Based
ma'am.
on our given input features,
Anita
we can
ma'am.
predict the data. So second case, we are getting it as a 5. So
Hello,
that indicates
Anita
all the
ma'am.
4 bits has been broken.
Ma'am, please mute, ma'am.
You can load the data. So we are getting our Simulink based digital twin model. Once we here enter the values, we will get the results. Either you can make use of this Simulink model or you can use your own GUI. You have to enter all the 10 features. Once you run the model, we get the result. So in this case, we know our faulty conditions. If it is for real-time computations, the faulty conditions we are not knowing. Once we give the features, the system will predict that whether it having the first tool or 1T broken or 2T, 3T or catastrophic failure too. It gives the class condition as 1, that seems true. So this methodology can be proposed to monitor the tool conditions. So rather than the classification problem, if you want to make it as a regression, so you have to measure the tool wear for every 1 hour and we can build a regression model. So from the regression model, we can estimate the RUL estimator, the kind of degradation model or direct model. So from there, how many hours it has to work further, we can identify its remaining useful life. So based on that, we can replace the tool on time, or if required, we can procure the tool without making any delay. So the different algorithms give different classification accuracies. So hyperparameter tuning of algorithm is essential one. Since our entire digital twin model relies on the ML algorithm, so the algorithm has to work without any underfitting or overfitting. So further, we can apply this for any kind of real-world applications, not only in the tool condition monitoring or tool layer classifications. It can be useful for other machine applications also. So if we are having adequate software facilities, we can make our entire plant or entire process in terms of digital twin. We can monitor it anywhere. So meanwhile, in the component level or the system level, we can identify its remaining useful life or where at when it has to reaches its failure or when it reaches some maintenance activity. Everything can be predicted well in advance. So this digital twin, we can make it as a two-way possible use of physics as well as our digital data-driven approach. So based on our convenience and the available resources, we can make a digital twin. So have any queries?
Professors, any queries? Professors, any queries? Sir, I have a doubt, sir.
Yeah, please, ma'am.
Sir, is it implemented in India, sir?
Oh, yes, ma'am. In Coimbatore, also few industries they have deployed digital twin for
Yes, sir.
monitoring.
Okay, sir.
One pump industry currently they have deployed to the digital twin.
Okay, sir. Professors, if you have any queries, please post in the chat box. See to you, ma'am. Please wait. Sir, we have a question from how it shaped future and how it can be integrated in the curriculum.
But for future of digital twin, we can create any model or we can make an entire plan based on the digital twin. So once our digital twin model is ready, we can monitor and make any suggestions or corrections in anywhere, as like our IoT based things. And the for curriculum point of view, we can add a course on digital twin. Students can able to create a digital twin and visualize the data, and they can able to model it.
Professor, the feedback link is working. Please check it now. Any other queries? So, do we have any open source software for this digital twin, sir?
And currently there is no open source software.
Okay.
From Siemens, we have a software that will be proprietary one. Instead of going with that, if you are having MATLAB, we can have a digital twin model now.
Okay, sir.
We start with small components, then move on to the system level, then move on to the systems of system.
Okay, sir.
For simplest way, we can start with prediction of deformation or diffraction in simple cantilever beam that can be easily modeled with MATLAB as well as FEA. We can get the measurements in terms of stress and deformation. The physical model, we can attach strain gauge or any kind of sensor to measure the deformation also. That can be integrated with our model to get the actual data.
Thank you, sir. Professors, any other queries? Professors, any queries? Sir, can we include this for the mechatronics curriculum, sir, or which department is preferable for this digital twin, sir?
But mechatronics is most suitable.
So it includes all the departments. So this is
Mechatronics,
preferable.
instrumentation, automation branches can include digital twin as one of the core courses. During the 6th semester or 7th semester, they can learn it now.
Okay, sir.
various domains for digital twin. You can use it for manufacturing, factory automation, different robots. It's actually suitable for multidisciplinary field also, ma'am. For example, in our house, we are having any small devices that can also convert it into digital twin model. We can monitor its performance in anywhere.
Professor, any other queries? So queries. Can we end the session, sir?
Gosh, yes.
Professor? So it is a wonderful session, sir. So we have gained good knowledge about digital twins and the application related informations. So this is the current trend of the day. So we gain lot of information about this digital twin. So it is very helpful for our teaching fraternity. Thank you, sir.
Thanks a lot, ma'am. I would like to express my sincere thanks to head of the department, the coordinator Guneshwari ma'am, and other faculty coordinators and the participants from all the institutes. Thank you all.
Thank you, professors. We can have the afternoon session by 2. Thank you all.
Thank you, professors and esteemed faculties. Everyone are requested to join the meet at 1:45 p.m. today for afternoon session. Thank you.